Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Cosmic Titans, the unseen architects of the early universe. In the earliest epochs of the universe, when the cosmos was young and still emerging from the primordial fireball, conditions were set for the creation of enigmatic entities that would come to dominate the centers of nascent galaxies. The interplay of gravity and the dense, turbulent medium of gas and dark matter provided the ideal environment for the rapid collapse of matter into compact regions, eventually giving birth to the first supermassive black holes. These objects, with masses millions to billions of times that of the Sun, began as seeds formed by the collapse of primordial gas clouds under conditions that defied the typical cooling processes seen in later epochs. The extreme density and high temperatures in these early regions allowed gravitational instabilities to overcome pressure support, leading to a runaway collapse that produced these colossal gravitational wells at a pace much faster than standard stellar evolution would predict. The formation mechanisms behind these supermassive black holes have long been a subject of intense theoretical exploration and debate. Researchers have proposed several models, ranging from the direct collapse of massive gas clouds that bypass the traditional stages of star formation to the aggregation of remnants from the first generation of stars, known as population 3 stars, whose short lifespans and explosive deaths may have provided the necessary conditions for rapid mass accumulation. In this embryonic universe, where the chemical composition was remarkably simple and cooling channels were limited, the efficiency of these processes was significantly enhanced, allowing for the swift growth of black hole seeds. The extraordinary mass these seeds could achieve in such a brief cosmic time frame suggests that they were not mere byproducts of stellar evolution, but fundamental players in the unfolding narrative of structure formation. Observational evidence from deep sky surveys and high-redshift quasars offers compelling support for the existence of these early supermassive black holes. Distant quasars, which shine with an intensity that can outmatch entire galaxies, are understood to be powered by the accretion of matter onto supermassive black holes. Their detection at epochs when the universe was less than 1 billion years old indicates that the process of black hole growth must have been both efficient and remarkably rapid. The intense radiation emitted during these early accretion phases not only provides clues about the physical processes occurring in the vicinity of the black hole but also influences the surrounding intergalactic medium, potentially playing a role in the reionization of the universe. This period of reionization marks a fundamental transition in the cosmic landscape, setting the stage for the formation of later structures and the evolution of galaxies as we observe them today. The early supermassive black holes, acting as gravitational anchors, were likely instrumental in shaping the morphology and dynamics of the first galaxies. Their immense gravitational pull could have orchestrated the infall of gas and dark matter, facilitating the assembly of galactic structures and initiating a complex interplay between accretion processes and feedback mechanisms. The energy released from matter spiraling into these black holes would have generated powerful outflows and radiation, impacting star formation in the surrounding regions and contributing to the turbulent conditions observed in young galaxies. These processes, occurring on scales both local and cosmological, hint at a symbiotic relationship where the growth of black holes and the evolution of galaxies were inextricably linked from the very beginning of cosmic history. In the early cosmos, the influence of supermassive black holes extended far beyond their central positions, as their voracious accretion processes and prodigious energy outputs began to actively shape the surrounding galactic environments. As matter spiraled into these titanic objects, enormous amounts of electromagnetic radiation were liberated from the regions surrounding them, permeating the host galaxies and dramatically altering the conditions within. This intense energy output, manifesting in the form of powerful outflows and high-velocity jets, played a critical role in regulating the supply of cool gas necessary for the birth of new stars. By injecting heat and momentum into the interstellar medium, these active cores imposed a self-regulatory mechanism on their galaxies, occasionally suppressing star formation through the inhibition of gas cooling, while in other instances compressing nearby clouds and sparking localized bursts of stellar birth. The energetic feedback from these central engines influenced the dynamics of gas on scales that reached well beyond the immediate vicinity of the black holes, affecting the evolution of entire galactic halos and even the larger cosmic structures that interconnected these early systems. In the chaotic environment of the primordial universe, the interplay between supermassive black holes and their host galaxies was further intensified by frequent mergers and interactions. Collisions between young galaxies, common in these formative epochs, funneled copious amounts of gas into central regions, thereby intensifying the accretion activity of the resident black holes. This episodic delivery of material initiated cycles of vigorous activity followed by quieter phases, a rhythmic pattern that left distinctive signatures in the light emitted by these active galactic centers. These cycles of activity not only contributed to the rapid buildup of black hole mass but also played a significant part in driving the overall evolutionary pathways of the galaxies that harbored them. The dynamic processes at work during these mergers led to complex behaviors in both the stars and the gas, ultimately contributing to the diverse morphologies observed in galaxies as the universe matured. At the same time, the energetic phenomena associated with these active cores had a profound impact on the broader intergalactic environment. The powerful radiation and winds emanating from the central regions were capable of altering the chemical and physical state of the gas that pervaded the space between galaxies. This energy injection fostered the mixing and dispersal of heavy elements, gradually transforming the pristine, nearly metal-free medium of the early universe into a richer, more chemically diverse milieu. The enhanced distribution of these elements facilitated the cooling of gas over large scales, setting the stage for the subsequent formation of new stars and galaxies. In this manner, the influence of supermassive black holes resonated well beyond their immediate host systems, contributing to the overarching evolution of cosmic structures and influencing the conditions that would govern future generations of celestial bodies. Throughout these processes, the actions of supermassive black holes served as a critical nexus in the cosmic evolution narrative, linking the growth of individual galaxies to the large-scale development of the universe. Their ability to regulate and even reshape the distribution of matter and energy in their surroundings highlights a fundamental aspect of early galactic evolution, wherein the energy output from the cores acted both as a catalyst for change and as a controlling force. By driving turbulence in the interstellar medium and initiating both the suppression and stimulation of star formation, these central objects orchestrated a delicate balance between the competing forces of collapse and expansion. Their profound impact is evidenced by the observable differences in the physical and chemical properties of galaxies across vast cosmic distances, offering clues about the intertwined evolution of black holes and the cosmic structures they inhabit. In the vast expanse of cosmic history, the influence of early supermassive black holes extends well beyond the immediate processes of accretion and feedback, reaching into the realm of large-scale structure formation and the underlying fabric of the universe itself. These primordial giants, forged in the turbulent conditions of the young cosmos, played an essential role in the sculpting of the cosmic web by interacting with the pervasive dark matter and influencing the gravitational dynamics that govern mass distribution on grand scales. Their mergers and coalescences, driven by the inexorable pull of gravity, set in motion a cascade of events that not only amplified their own mass but also contributed to the assembly of the vast, filamentary structures that define the modern universe. In the unfolding narrative of cosmic evolution, the violent collisions between these massive objects generated gravitational waves, subtle ripples in spacetime that carry with them the imprints of ancient interactions. These signals, now emerging as a promising field of study with next-generation detectors, hold the potential to unveil the hidden histories of black hole mergers and offer direct insights into the dynamics of the early universe. The intricate interplay between these colossal entities and the dark matter halos that enveloped them forged a symbiotic relationship, one that influenced the subsequent formation of galaxies and clusters. As these black holes grew through successive mergers, their gravitational influence reshaped the distribution of matter, creating localized regions of enhanced density that would later evolve into the sprawling galactic structures we observe today. The energetic processes associated with their accretion activities may have also seeded and amplified cosmic magnetic fields, which, in turn, played a role in guiding the flows of gas and in shaping the evolution of nascent galaxies. This complex feedback between supermassive black holes and their cosmic surroundings highlights the profound interconnectedness of astrophysical phenomena, linking the physics of extreme environments with the overarching patterns of cosmic structure. In theoretical models and numerical simulations that aim to capture the evolution of the universe from its earliest moments, the imprint of these early supermassive black holes emerges as a critical factor in determining the fate of matter on both local and intergalactic scales. The simulations indicate that the gravitational interactions and energetic outbursts from these objects could trigger turbulence and induce pressure variations in the intergalactic medium, setting off a chain reaction that influenced the cooling, condensation, and eventual star formation in surrounding regions. Such processes underscore the idea that the legacy of these ancient black holes is woven into the very fabric of cosmic history, with their influence resonating through billions of years to affect the distribution and evolution of galaxies across the observable universe. The continuing refinement of observational techniques, particularly in the realm of gravitational wave astronomy and deep sky surveys, promises to unlock further secrets of these enigmatic titans. As researchers gather more data and enhance the precision of their models, the role of early supermassive black holes in dictating the large-scale architecture of the cosmos becomes increasingly apparent. Their legacy, encoded in the patterns of galaxy clusters and the subtle undulations of spacetime itself, is a testament to the profound impact that these early behemoths had on the evolution of the universe. The insights gleaned from these studies not only deepen our understanding of fundamental physics but also offer a glimpse into the dynamic and interconnected processes that have shaped the cosmos from its earliest moments to the intricate structures we witness today.